This is the power rule of integration, also sometimes called the reverse power rule, because it's just like the power rule for derivatives, but in reverse. Mastering the use of this rule to compute integrals takes a little bit of practice, and practice is exactly what we're going to get in today's video. We're going to complete all 20 of these integration problems, all using the power rule. You can see that most of these are definite integrals, where we have bounds to evaluate with, but the last 5 are indefinite integrals. For the definite integrals, we will also mention the indefinite integrals because it doesn't take much extra time. This video has chapters, so you can skip around the problems as you please. These definite integrals will take a very long time to simplify and evaluate, so if you don't need practice with that, be sure to use those chapters to skip around. Notice we'll have some problems where we have a variable in the denominator. We also have various problems with roots and radicals. We also have problems with multiplication, and we even have a couple of absolute value problems. So it gives you a really good sense of how to do this in any situation. And at the end, I'll give you a set of challenging bonus problems for you to try on your own. Let's get into it. Let's begin with problem 1, the integral of 5x from 0 to 2. The power rule for integration tells us that to integrate x to the n, all we have to do is increase x's power by 1 and then divide by that new power. It's just the power rule for derivatives in reverse. Now in this case, we also have this factor of 5, but factors just hang out. It's going to get multiplied by everything, no big deal. So this integral is, in brackets, the power of x right now is 1. So we have to increase it by 1 so that it becomes a power of 2. Now, the coefficient of 5 we still need, but we also have to divide by the new power. So it's 5 over 2. Now, we would have a plus c if this was the indefinite integral, and we would be done, but it is a definite integral. So we need to evaluate this from 0 to 2. Once more, what did we do? We increased the power of 1 by 1, so we bumped it up to 2, and then divide by that new power, divide by 2. So that coefficient of 5 that we had is getting divided by 2. All right, now we evaluate this from 0 to 2. So first, we'll plug in the upper bound of 2. So this is 5 halves multiplied by 2 squared. We're plugging in 2 for x. And then subtract, plugging in the lower bound. If you plug in 0, you'll just get 0. So this is just 5 halves times 2 squared minus 0. That's 5 halves times 4. So this is 5 halves times 4. And 4 over 2, those are going to cancel out and just leave a factor of 2 behind. You could also think of this as just 20 over 2. Either way, it is 10, and that is our final answer. Moving on then to problem 2, the integral of 3 with respect to v from 4 to 9. Now in this case, we don't have a variable anywhere, right? We're integrating with respect to v, but we don't see any v in the integrand. If you really want to think about this as the power rule, we can put a v here. Since we don't see a v, we could write one with a power of 0. Since anything to the power of 0 is 1, this would be like having no v there at all. This allows us to use the power rule. We have to increase the power of v by 1, so instead of v to the 0, we now have v to the 1, and then divide by that new power. Dividing by 1 doesn't do anything, so we just keep that original coefficient of 3, and we're evaluating this from 4 to 9. If this was an indefinite integral, we'd just throw on a plus c and we would be done, but we're going to have to go through with the evaluation from 4 to 9. Also remember, we're evaluating these basic integrals by finding antiderivatives. 3v is the function whose derivative is 3, and that's why the integral works out this way. The derivative of 3v is 3. So this is an example where it's kind of overkill to think about the power rule, but I'm just showing you can apply the power rule here. It still works as usual. Let's proceed with the evaluation. We plug in the upper bound of 9, so 3 times 9, and then subtract, plug in the lower bound of 4, so minus 3 times 4. 3 times 9 is 27, so this is 27 minus 3 times 4, which is 12. So our final answer is 15. Moving on to problem 3, the integral of 2x minus 1 from -1 to 0. Now, let me take this moment to remind you what the integral actually is, right? We don't want to lose sight of the fact that this is the area under the curve. In this case, the integral from 2x minus 1, that's the area between the line 2x minus 1 and the x-axis. 2x minus 1 is a line of slope 2 and a y-intercept of -1, so that might look something like this, and we are computing the area between this line and the x-axis from -1 to 0. So that's this area here from -1 to 0, and the region would look something like that. Because this area lies completely below the x-axis, this is going to be a negative area. So when we calculate this, we're going to get a negative answer. Anyways, let's proceed. Again, we're using the power rule. There are two terms in this integrand, 2x minus 1. They can just be integrated individually. There's no significant complication here. So let's just proceed. We'll open up the brackets and start to apply the power rule. The exponent of x is 1. So we have to increase it by 1 to a power of 2. The coefficient of 2 we still have, but then we also have to divide by the new power. The new power is 2, so we divide by 2. Now, integrating -1, think about the antiderivative. What function has a derivative of -1? The answer is just -x. The derivative of minus x is -1. So there we go. If this was an indefinite integral, we'd add a plus c and we'd be done. But it's a definite integral, so we're going to have to finish by evaluating with these bounds. Before we do this computation, the 2/2, of course, is 1, so we might want to just get rid of it. We don't have to write 2/2 there. This is our integral. Let's start to evaluate. Plug in the upper bound first. That's going to give us 0 squared minus 0. Of course, we don't have to write this. It's just 0. I'm writing it for the sake of detail, though. Then we plug in -1. So -1 squared. Again, this is the lower bound, so we're subtracting this. -1 squared minus -1. All right, you want to be real careful with your signs, right? Because you could easily make a mistake here. This guy at the front just zeroes out. Don't forget about the negative here. So this is going to be negative. -1 squared is +1. And then minus -1 is +1. Final answer, -2. Like we expected, our final answer is negative. All right, let's go ahead and move on to problem 4, the integral of t squared minus 2 from -2 to +2. This will be a lot like the previous problem. If you want a quick sketch here to remember what we're doing, we're finding the area under the curve. T squared minus 2, that's an upwards facing parabola moved down 2 units. So it looks something like this, and we're integrating this from -2 to +2. -2 might be like over here, +2 might be over here. So the area we're finding is actually some positive, some negative, and some positive. From this sketch, it looks like the negative area outweighs the positive area, but it's just a quick sketch, so we might be wrong. The area might be positive, it might be negative. Let's do the integral and find out. We'll just apply the power rule. So increase the power of t by 1. It did have a power of 2, but now it will have a power of 3. Then divide by the new power. So divide by 3, which is the same as multiplying by a third. Then for constants, just think about the antiderivative. What function has a derivative of -2? Well, since we're integrating with respect to t, that would be -2t. The derivative of -2t is -2. Again, you can use the power rule for these constants by writing in a t to the power of 0, but that really seems like more work than necessary. You'd then do a plus c if we wanted an indefinite integral, but since we're doing a definite integral, we'll close the brackets and evaluate from -2 to +2. Begin by plugging in the upper bound of +2, so this is going to be 1/3 times 2 cubed, and 2 cubed is 8, so let's write that. And then minus 2 times 2, or -4. Then subtract, plugging in the lower bound. So we're going to have 1/3 times negative 2 cubed. Negative 2 cubed is negative 8. And then subtract 2 times negative 2. That's the same as adding 4. Now, in this first set of parentheses, we have 8/3 minus 4, which is 12/3. So in total, it's negative 4/3 in the first set of parentheses. And then we're subtracting. 1/3 times negative 8 is negative 8/3. And then plus 4 is plus 12/3. So negative 8/3 plus 12/3. In total, that's going to be 4/3. So minus 4/3. You can see our sketch happened to be correct. There was more negative area because our final answer is negative 4/3 minus 4/3. So minus 8/3. Moving on now to problem 5, the integral of 4 over x cubed minus 1 from 1 to 2. This is the first one where we're going to want to rewrite it before we proceed with the integral, because we don't want x's stuffed in the denominator when we're trying to apply the power rule for integration. After you've had some practice, you probably wouldn't have to do this rewriting, but for now, it's going to be an important part of giving you a detailed instruction. So, want to make sure you know what it means to have a variable in the denominator. Having x to the third in the denominator is the same as having it in the numerator, but with a negative power, right? We can just move this guy to the numerator, where we would like it for this purpose, by changing the sign of its exponent. Since the sign was positive, now the sign is negative, and we've got it out of the fraction. And the minus 1 we don't have to change. So these are the same thing. Don't forget your dx. Now we can proceed with the power rule as usual. So we're going to increase the power of x by 1. Be careful, a lot of people make mistakes here with the negative powers. The power is negative 3. If you add 1 to negative 3, you're going to get negative 2. Now our coefficient of 4 we still have. The power gets bumped up to negative 2. And then we have to divide by the new power. So the coefficient of 4 gets divided by that new power of negative 2. Now, what function has a derivative of negative 1? That would just be negative x. So there you go. Plus c if this was an indefinite integral, but it's not, so close the bracket. We're evaluating from 1 to 2, and let's start to evaluate this, although we might as well simplify first. 4 over negative 2 is the same as negative 2, so I'll just replace that with negative 2. Plugging in the upper bound of 2, we're going to have negative 2 multiplied by 2 to the negative 2, and then minus 2. Then we have to subtract, plugging in the lower bound of 1. Plugging in the lower bound of 1 gives us negative 2 multiplied by 1 to the negative 2 minus 1. Now you can see if you're not quick with your arithmetic and negative exponents, this stuff can start to take a really long time. 2 to the negative 2 is 1 over 2 to the 2, or 1 over 4. So this is negative 2 over 4, so negative 1/2. Negative 1/2 minus 2 is negative 2.5, which is negative 5/2. So that just evaluates to negative 5/2. And then we're subtracting this guy. The 1 doesn't do anything, right? So this is just minus 2 minus 1, so minus 3. Now minus 3 is the same as minus 6/2. So this is minus 5/2 minus negative 6/2. That's the same as minus 5/2 plus 6/2. So our final answer is a nice 1/2. Let's move on now to problem 6. The integral from 1 to 4 of u minus 3 divided by the square root of u. This is another example where we will have to do a little bit of rewriting before we proceed with the integral. We have a fraction, and we can split this fraction across the subtraction that takes place in the numerator. So we can rewrite this as u divided by root u minus, separately, 3 over root u. Now we'll just have to simplify exponents with this term on the left, and on the right, we're in a situation very much like we were in problem 5. We should also write du here, and you may want to put this expression in parentheses so it's clear that this whole thing is being integrated. Beginning with this term on the left and simplifying the exponents, in the numerator we have u to the 1, and in the denominator we have the square root of u, which is the same as u to the 1/2. So, because this is division, we have to subtract the exponents. The exponent of 1 minus the exponent of 1/2 that's in the denominator. So this becomes just u to the 1/2 power, which is the same as root u, but it's easier to integrate it if we write it like that. As far as this term on the right goes, again, the u in the denominator has a power of 1/2, so we can bring it to the numerator by making that power of 1/2 negative. And there we go. Again, I'll just put this guy in parentheses and then write the du. We're integrating with respect to u. Now we can proceed with the integration. Just use the power rule. U to the power of 1/2, we have to increase that power by 1. Adding 1 to 1/2 is the same as adding 2/2 to 1/2. So if we increase it by 1, it becomes a power of 3/2. The pattern here, which you would get with practice, is that you really just have to add the denominator to the numerator. That's how you increase a fraction by 1. Remember, we have to divide by the new power. Dividing by 3/2 is the same as multiplying by its reciprocal, 2/3. All right, on to the next term. With the negative exponent of 1/2, again, we have to increase it by 1, so just add 2/2 to it. Negative 1/2 plus 2/2 is positive 1/2. So we have minus u to the positive 1/2. We also have this coefficient of 3, and remember, we need to divide by the new exponent. Dividing by 1/2, I guess I'll write it like that, divide by 1/2, although you should recall that's the same as multiplying by 2. So we'll be able to simplify this a little bit. We would just write plus c if this was an indefinite integral, but it's not. It is a definite integral that we're evaluating from 1 to 4. So we'll start the evaluation now. Let's start by plugging in the upper bound of 4. So we have 2/3 multiplied by 4 to the power of 3/2. And then we're subtracting. 3 over 1/2 is the same as 3 times 2, so that's 6. Again, we're plugging in 4, so we have 4 to the power of 1/2, and that's it. Now we have to subtract, plugging in the lower bound, which is 1. Plugging in 1 is straightforward because 1 to the 3/2 is just 1, and 1 to the 1/2 is just 1. So this just ends up being the difference of the coefficients. So 2/3 minus, again, 3 over 1/2 is 6. Now let's carefully finish this computation. 4 to the 3/2, you should think of rational exponents like this as doing two things. The denominator of 2 acts as a square root, and the numerator of 3 just means to cube it. So the square root of 4, well, that is 2. And then you have to cube it, which is 8. So this is 2/3 multiplied by 8, and then minus this power of 1/2 is just a square root. The square root of 4 is 2. So this is 6 times 2. And then we are subtracting 2/3 minus 6. 6 is the same as 18/3. So this is 2/3 minus 18/3, which is negative 16/3. Notice I'm using quite a few parentheses here. I'm trying to be careful. It's really easy to make a sign error when you're doing this stuff. 2/3 times 8, that is 16/3. And then minus 6 times 2, so minus 12. And then minus negative 16/3, so plus 16/3. 16/3 and 16/3 adds to 32/3. And how many thirds are in 12? Well, that would be 36. So we are subtracting 36 thirds. Sorry, still a little sick. So final answer, negative 4 thirds. Hopefully you notice at this point that it's really the evaluation, all that arithmetic at the end of these problems that takes the most time. The real integration part is actually pretty easy once you get the hang of it. Let's move on to problem 7. This is the integral of x to the 1/3 from negative 4 to positive 4. Now, this one we can jump straight into the power rule. We have to add 1 to that power of 1/3. 1/3 plus 1 is 1/3 plus 3/3. Again, it's like you're just adding the denominator to the numerator. So that comes up to 4/3. We have x to the 4/3, and then divide by the new power. Dividing by 4/3 is the same as multiplying by the reciprocal 3/4. And then we're evaluating this from negative 4 to positive 4. Let's start by plugging in the upper bound of positive 4. So we have 3/4 multiplied by 4 to the power of 4/3, and then subtract, plugging in the lower bound. So minus 3/4 multiplied by negative 4, we're plugging in now, to the power of 4/3. Now notice we can actually get rid of this negative in front of the 4 because the power is 4/3. That denominator of 3 is like a cube root, but the numerator of 4 is like a power of 4. That's an even power. So this negative is actually just going to go away in the end anyways. And so you can see we have this thing minus itself. And so the answer is 0, which geometrically should not be surprising, because this is the area between x to the 1/3 and the x-axis. If you know what x to the 1/3 looks like, it's something like this. It is symmetric about the origin. It's a 180-degree rotational symmetry. When we integrate from negative 4 to positive 4, we have all this negative area that gets exactly canceled out by the positive area. So our answer is 0. This is what's called an odd function. Let's move on now to problem 8, the integral of the cube root of t minus 2 from negative 1 to positive 1. We'll begin by rewriting this so we have t to some power, and then we can apply the power rule. The cube root of t, you should know, is just t to the power of 1/3. Just like the square root is a power of 1/2, a cube root is a power of 1/3. And then minus 2, we don't need to change that. This integral is with respect to t. Let's proceed then with the power rule. Increase the power of t by 1. If we increase 1/3 by 1, it becomes 4/3, so t to the 4/3. We then have to divide by the new power, which is the same as multiplying by its reciprocal. Dividing by 4/3 is the same as multiplying by 3/4. Then think about the antiderivative. What function has a derivative of negative 2? Well, since we're integrating with respect to t, that would be negative 2t. Then you would just write plus c if this was an indefinite integral, but it's not, so we're going to put the bounds here. We're integrating from negative 1 to positive 1. Let's begin by plugging in the upper bound. We're going to have 3/4 multiplied by 1 to the 4/3 is just 1, so we don't really have to bother writing it. And then minus 2 times 1, so just minus 2. And then subtract, plugging in the lower bound. Plugging in the lower bound, we have 3/4 multiplied by negative 1 to the 4/3. Just like the previous example, the negative will cancel out because of this power of 4 in the numerator, and so this would just be 3/4. And then minus 2 times negative 1. Wrapping up this computation, we have 3/4 minus 3/4, so those guys cancel out, and then we have minus 2 minus positive 2. So that's going to be minus 4. That's because this here, negative 2 times negative 1, that's positive 2, right? So we're actually subtracting positive 2 from negative 2. Final answer, negative 4. Notice how this is different from the previous example. In the previous example, we had an odd function, and since we were integrating from negative 4 to positive 4, the negative area exactly canceled out with the positive area. This function, the cube root of t minus 2, is just like this one, x to the 1/3, but it's shifted down 2 units. So some of the area that would have been positive in this example is now actually negative in this example because the function got shifted down below the x-axis. Moving on now to problem 9, the integral of the square root of 2 over x from 1 to 5. Again, we're going to start by rewriting this. The square root of a fraction is the same as the fraction of the square roots. By that, I mean that we can rewrite this as root 2 over root x. And of course, this is with respect to x. Now, if you have a factor like root 2, you can just take that out of the integral if you like. So I'm just going to bring that out. This is root 2 multiplied by the integral from 1 to 5 of 1 over root x. But remember that root x is the same as x to the 1/2. So we can bring this out of the fraction if we just make its power negative, x to the negative 1/2. And we're integrating with respect to x. Again, that's because a square root is the same as a power of 1/2, but because it's in the denominator, we have to make it negative to get it out of the fraction. Now that we have just some power of x, we can go ahead and integrate. Don't forget the root 2 that we still have out front. And then we have to increase this power by 1. So add 2 halves. Negative 1/2 plus 2 halves is positive 1/2. So x to the positive 1/2. Then divide by the new power. Dividing by 1/2 is the same as multiplying by 2 over 1, or just 2. Then it would just be plus c if this was an indefinite integral, but it's not, so we're going to evaluate this from 1 to 5. Thus, we have the square root of 2 multiplied by, plugging in the upper bound, we have 2 times 5 to the 1/2. 5 to the 1/2 is just root 5. And then minus, plug in the lower bound. 1 to the 1/2 is just 1, so this is just 2 times 1, or just 2, that we are subtracting. All right, and then we could distribute the root 2 if you like. That's going to be 2 times root 5 times root 2, which is just root 10, and then minus 2 root 2. You could factor a 2 out of this if you like. I'm just going to leave it as is, and we'll move on to the next example. On to problem 10, the integral of 2 minus t times root t from 0 to 3. We're going to start by trying to rewrite this integrand, so it's just t to some power, and in this case we'll have multiple terms, but that's no big deal. So what we're going to do is rewrite the root t as t to the 1/2, and then distribute it through these parentheses, through that 2 minus t term. So we have 2 minus t, and then multiplied by root t is just t to the 1/2. Okay, now we can do the distribution, which will require use of our exponent laws. First, we have t to the 1/2 times 2, so just 2t to the 1/2. Then, t to the 1/2 times minus t. Minus t has an exponent of 1, so just add the exponents together, since they're getting multiplied. 1 plus 1/2, that's 2 halves plus 1/2, so 3 halves. And don't forget the minus. So minus t to the 3 halves. And I'll put this in parentheses. This integral is with respect to t. Now that we just have powers of t, we can proceed with the power rule. So we'll open up the brackets. We'll have to increase the power of t by 1. Adding 1 to 1/2 gives us 3 halves. So we have t to the 3 halves. Then we need to divide by this new power. Dividing by 3 halves is the same as multiplying by 2/3. But we also have this coefficient of 2 that still needs to be there. So it's 2 times 2/3. Then let's move on to the next term. T to the 3 halves. We have to increase its power by 1. 3 halves plus 2 halves is 5 halves. So the new power is 5 halves. Then we have to divide by the new exponent. Dividing by 5 halves is the same as multiplying by the reciprocal 2/5. We would just write plus c if this was an indefinite integral, but it's not. We're going to evaluate it from 0 to 3. First, plugging in the upper bound of 3. 2 times 2 over 3, let's write that as just 4 over 3, and then we plug in 3. So 3 to the power of 3 halves. Minus 2/5 times 3 to the power of 5/2. Then we can plug in the lower bound, but actually if we plug in 0, all of these terms are just going to be 0, so we don't have to worry about that. This is the answer. There is a little bit of work we could do here. 3 to the 3/2 on the left divided by 3, right? We have this division by 3 also. We could simplify this by just subtracting the exponents. This is an exponent of 3/2. It's getting divided by 3 with an exponent of 1, so subtract the exponents. 3/2 minus 1 is 3/2 minus 2/2, which is just 1/2. And then we can get rid of that 3 because we just divided it. So this looks a little bit nicer. This term has a 3 to the 1/2, and this term also has 3 to the 1/2. It happens to have 3 to the 5/2, but 3 to the 1/2 is part of that. So if you wanted to, you could factor out 3 to the 1/2. This term also has a factor of 2, as does this one. So in fact, we could factor out 2 times 3 to the 1/2, although 3 to the 1/2 is just root 3. So we could factor out 2 root 3. That would leave this as 2, because this times this is this, and then minus 1/5 multiplied by 3 to the 4/2, because we took out 3 to the 1/2, but 3 to the 4/2 is just 3 squared, which is actually just 9. So 1/5 times 9, but that's just 9/5. So 2 minus 9/5. How many fifths are in 2? Of course, that's 10/5. So this is 10/5 minus 9/5, which is 1/5. So final answer, we're actually able to clean this up quite a bit. Final answer is 2 root 3 over 5. Again, you can see the computing at the end and the simplification definitely takes up the bulk of the time. Let's move on to problem 11. This is the integral from -3 to 0 of w to the 1/3 minus w to the 2/3. And we're just going to jump straight into the application of the power rule here because we have powers of w, so we're good to go. Let's increase the power of 1/3 by 1. 1/3 plus 3/3 is 4/3. So this is w to the 4/3. Then divide by the new power. Dividing by 4/3 is multiplying by 3/4. Then we have to subtract this guy. We're going to increase the power by 1. 2/3 plus 3/3 is 5/3. So this becomes w to the 5/3. And then divide by the new power. Dividing by 5/3 is the same as multiplying by 3/5, and we're evaluating this from -3 to 0. Now, when we plug in the upper bound of 0, both of these terms are actually just going to go away. So all we have to do is subtract the evaluation at the lower bound. Plugging in the lower bound, we have 3/4 multiplied by -3 to the 4/3, and then minus 3/5 multiplied by -3 to the 5/3. Now, all three of these negatives are actually going to go away. This is a situation we've seen several times. We have a negative with an even power in the numerator, so that negative is going to cancel itself out. This guy does not have an even power, so this negative would stay, but it's being subtracted, so those will actually cancel out in the end also. After getting rid of the negatives in the parentheses, there's some more work we can do with the 3's here. 3 to the power of 1 times 3 to the 4/3 is just 3 to the 7/3. So this is going to be negative. We'll have the 1/4 still, but we're combining the 3's. So 1/4 multiplied by 3 to the 7/3. Similarly, 3 to the power of 1 multiplied by 3 to the 5/3 is 3 to the 8/3. We'll still have the 1/5 hanging out here, and then multiplied by 3 to the 8/3. Now, both of these terms have 3 to the 7/3. This one has 3 to the 8/3, but it also has 3 to the 7/3 as part of that. So let's factor out 3 to the 7/3. And there is our hideous final answer. -3 to the 7/3, we factored this guy out, leaving behind 1/4, plus there was still a 3 to the 1/3 left over, which is cube root of 3, multiplied by a fifth, or divided by 5. And There you go. Moving on now to problem 12, the integral from -8 to -1 of x minus x squared all over 2 times the cube root of x. All right, so this looks like a little bit of a mess, but we're just going to have to begin with some rewriting as usual. We'll split the fraction across the subtraction in the numerator. We'll also rewrite the denominator that has a cube root of x as x to the 1/3. Also, this 2 in the denominator, we can just bring out of the integral as a factor of 1/2. So doing all of this, again, we're splitting up the fraction. So we're going to have x over the cube root of x, which is just x to the 1/3, minus x squared over the cube root of x, which is just x to the 1/3. This is being integrated with respect to x, and we might want to put this in parentheses. Now we just have to simplify these exponents. Since there is division taking place, we'll just have to subtract the exponents. So in the first term, we have x to the 1 divided by x to the 1/3. So subtract the exponents. 1 minus 1/3, that's just going to give us x to the 2/3. Then we are subtracting x squared divided by x to the 3rd. X squared, of course, is the same as x to the 6/3, and 6/3 minus 1/3 is 5/3. So this is minus x to the 5/3. Now that we have this written with just powers of x, we can proceed with the power rule. So we have 1/2, and then we'll increase this power of 2/3 by 1, which means we're adding 3/3 to that power. So this is going to be now x to the 5/3. Then we must divide by the new power. Dividing by 5/3 is the same as multiplying by the reciprocal, 3/5. And then subtract x to the 5/3. We have to again add 1 to that, so add 3/3. So that's going to be x to the 8/3. We have to divide by the new exponent of 8/3, and that's the same as multiplying by 3/8. Then just add c if this was an indefinite integral, but it's not, so we're going to have to evaluate with these bounds from -8 to -1. Let's begin by plugging in the upper bound of -1. Doing that, we're going to have 3/5 multiplied by -1 to the 5/3. So -1 to the 5/3. Then we're going to subtract 3/8 multiplied by -1 to the 8/3. Since 8 is an even power, the negative is actually just going to go away. And so in the end, this would just be +1. So it would just be 3/8 times +1. So we'll just leave it as 3/8. Then subtract, plugging in the lower bound of -8. So we're going to have 3/5 multiplied by -8 to the 5/3. And then we're going to have to go ahead and move this down so we have room to complete this expression. 3/5 times -8 to the 5/3, and then subtract 3/8 multiplied by -8 to the 8/3. Again, this power has an even numerator of 8, so that negative is going to go away. I'll just erase that. This is 8 to the 8/3. And there we go. All right, let's start making our way through this simplification. We still have the 1/2 out front. Now, -1 to the 5/3, because the power has an odd numerator, this is just going to be -1. So it's just going to be -3/5 minus 3/8. -3/5 minus 3/8. Okay? And then we're subtracting what's going on in the parentheses here. We have -8 to the 5/3. Now, the denominator of 3 in this power is like a cube root. And the cube root of -8 is -2. So this is just -2 to the power of 5. So we have 3/5 multiplied by -2 to the power of 5. Then subtract, similar thing going on here. We have 8 to the 8/3. The denominator of 3 in this power is like a cube root. The cube root of 8 is 2, so this is just going to be minus 3/8 multiplied by 2 to the power of 8. Now, since this fraction 3 over 8 is getting multiplied by 2 to the 8, I may think to write that denominator of 8 as 2 to the power of 3. Then we can actually do some exponent simplification here, because this is like 2 to the 8 divided by 2 to the 3, which is just 2 to the 5. So let's proceed with a little bit more simplification here. We have 1/2 multiplied by negative 3/5 minus 3/8. The common denominator there would be 40. So we would have minus 24 over 40 minus 15 over 40. And then we are subtracting. Negative 2 to the 5 is negative 32. And then we're multiplying that by 3, so negative 96. But that's being subtracted. So since we're subtracting a negative, it's actually positive. So positive 96 over that denominator of 5. We are distributing this negative at this point, so let's remember it also gets distributed over there. So that's also going to be addition. Again, 2 to the 8 over 2 cubed is 2 to the 5, just subtracting the exponents. So we have 3 multiplied by 2 to the 5. Again, 2 to the 5 is 32, so multiply that by 3 and you get 96. So this is just plus 96. Rather than combining all of these terms, I'm just going to worry about the fractional parts first. So let's think about this. 96 over 5. 5 goes into 100 20 times, so it goes into 96 19 times. This is actually the same as 19 and 1/5. So I'm going to put plus 19 plus 1/5. Now I can just worry about combining all of these fractions, and we can bring it all together at the end. I don't want to work with fractions that are needlessly large, those improper fractions. So let's go ahead and write this. We have 1/2 multiplied by negative 24 40ths minus 15 40ths is negative 39 40ths. Then we have plus a fifth. How many 40ths is that? Well, that would just be 8 40ths. So plus 8 40ths. And then we have 19 and 96. Those added together would be 115. This then is 1/2 multiplied by negative 39 40ths plus 8 40ths is negative 31 40ths. And then we are adding this to 115. This is a situation where it's probably easier to convert to decimals. Negative 31 over 40 is the same as negative 155 over 200, because 40 goes into 200 5 times, so we're just multiplying by 5 over 5. Now, if we reduce the numerator and denominator by a factor of 2, we'll have this in terms of hundredths, so we can write it as a decimal. Dividing the denominator by 2, of course, turns it into 100, and dividing the numerator by 2 turns it into negative 77.5. So, as a decimal, negative 31 over 40 must be negative 0.775. All right, let's try that as we proceed to rewrite this. This equals 1/2 multiplied by 115 minus 0.775. Now let's distribute the 1/2. So we'll have to cut both of these things in half. Cutting 115 in half gives us 57.5. So we have 57.5. And then we're subtracting. This guy divided by 2 is going to be 0.3875. Finally, subtracting these, it's actually pretty straightforward. It's just going to be 57.1125. And there's our final answer. Feel like I'm getting a headache after that one. Let's move on to our next page with problem 13. The integral from 0 to 4 of the absolute value of 3x minus 6. So we're doing an absolute value integral here. If you know what absolute values look like, they look something like this, right? So areas underneath absolute values are actually pretty easy to calculate geometrically because they're just right triangles. So it might be quicker if you were doing this problem to just do a sketch and find the area of a triangle. But we're going to evaluate this using the power rule. In order to do that, though, we need to figure out where the thing inside the absolute value switches between positive and negative, because the behavior of the absolute value depends on the sign of the thing inside of it. Now, of course, we can figure out where 3x minus 6 crosses 0 by just quickly setting up and solving the equation 3x minus 6 equals 0. Add 6 to both sides, so 3x equals 6, and okay, it must pass 0 when x equals 2. Now, on which side of that is it negative? Well, if we think about, here's a number line with x equals 2. To the left of x equals 2, we have values like x equals 0. And if you plug x equals 0 into 3x minus 6, clearly you get a negative. So to the left of that, the input is negative, which means the absolute value is going to multiply it by a negative in order to flip its sign to positive. That's what's happening all the way up to x equals 2. Now, to the right of x equals 2, you have things like x equals 3. If you plug x equals 3 into this expression, you get 9 minus 6, which is positive. So after that, the absolute value doesn't change the inside because the inside is already positive. It doesn't need to be changed. So we'll split the integral up into two things: the integral of this thing from 0 to 2, and then the integral of this thing from 2 to 4. I've just shrunk down this work. I'll leave it there if you want to take another look at it and think through that logic again. Remember, we're keeping in mind the original bounds from 0 to 4, but we're splitting it at 2, where the behavior of the absolute value function changes. So from 0 to 2, the thing inside the absolute value is actually negative, and so the absolute value switches its sign from 3x minus 6 to 6 minus 3x. That's from 0 to 2. Take that integral with respect to x. And then add the integral from 2 to 4. That's the rest of the area. And over here, this function inside the absolute value is positive. So the absolute value doesn't do anything to it. It's just the integral of 3x minus 6 dx. These would just be the areas of two triangles if you were doing this geometrically. Now we can proceed with the power rule. The function whose derivative is 6 is just 6x. And then minus 3x integrates to 3 over 2 x squared. That's increasing the power of 1 to 2 and then dividing by that new power. And this needs to get evaluated from 0 to 2. And then we're adding this other integral. 3x, we just did that. That integrates to 3 over 2 x squared. And then minus 6 becomes minus 6x. And we're evaluating this from 2 to 4. Plugging in the upper bound of 2 gives us 12. So I'll write 12 minus 3 halves times 2 squared is 3 halves times 4, which is 12 over 2, which is 6. So minus 6. And then we need to subtract, plugging in the lower bound. But the lower bound is 0, which just makes everything 0. So in fact, that's it. Let's just add this next part. All right, first, plugging in the upper bound of 4. 4 squared is 16, and 16 times 3 is 48. So this is 48 over 2. Well, that's just 24. So let's just write 24. And then we have to subtract 6 times 4, which is 24. Oh, wow, that works out pretty nicely. But then we have to subtract, plugging in the lower bound of 2. So that's going to be 3 halves times 2 squared, or 3 halves times 4, or 12 halves, or 6. And then plug in 2 over there. That's going to be minus 12. Finally, what we get is 12 minus 6, which is 6, plus 0. Okay, so we don't actually need that. And then minus 6 minus 12, which is minus negative 6, which is plus 6. So it's 6 plus 6, or 12. All right, on to number 14. This is going to be our final definite integral. Thank God, because these take so long. We are integrating from 0 to 4 the absolute value of x squared minus 3x plus 2. All right, this one is a little bit different from the previous one, but also pretty similar. Again, we have to ask the question, when does this thing inside the absolute value pass 0? Well, that amounts to just solving the quadratic equation, x squared minus 3x plus 2. Okay, well, let's just factor this guy. That's going to be x, let's see, it's going to have to be minus 2 and x minus 1. That way, minus 2 and minus 1 multiply to positive 2, and minus 2 and plus minus 1 add to negative 3 in the middle. So this equals 0. That means the quadratic is going to pass 0 at x equals positive 2 and x equals positive 1. So a quick sketch of this situation. We have an upwards facing parabola because the leading coefficient is positive, an upwards facing parabola that passes the x-axis at x equals 1 and x equals 2. So something like this, x equals 1 and x equals 2. So what happens is that from 1 to 2, the value of the function is negative. And so the absolute value function is actually going to reflect this part of the curve above the x-axis. It's going to hit it with a negative, and so, in fact, it's going to look like that. And I can just erase that piece that I drew previously. That's not actually going to be there because this is in the absolute value. So what we're going to have to do is split this up into three integrals. The integral of x squared minus 3x plus 2 from 0 up to x equals 1. For that whole time, the function is positive, and so the absolute value won't change it. But from 1 to 2, we'll have another integral where we hit this function with a factor of negative 1, because that's what the absolute value would do in order to change its sign to positive. And then from 2 all the way up to 4, we can just integrate the function because the absolute value won't change it because it's already positive. You can see a picture here is really helpful. As I write out this integral, it might be worth noting that instead of multiplying this function by negative 1 for the integral from 1 to 2, we could also just take that factor of negative 1 outside of the integral, so that instead of adding all these integrals together, we're actually subtracting this second one that goes from 1 to 2. This way, again, it's just like we factored that negative 1 out of the integral, which is totally fine to do. And again, that negative 1 factor comes from the absolute value function, which from 1 to 2 would be applying a factor of negative 1 in order to make the function positive. Finally, we have to add the integral from 2 to 4, where again the function is positive, so the absolute value is not going to do anything. Now notice all of these integrals are going to be the same, it's just the bounds that are different, plus the fact that we're subtracting this one in the middle. So let's go ahead and apply the power rule. You have to increase the power by 1 and then divide by the new power. So x cubed divided by 3. Throughout most of this video, we've been writing it like a 1/3 out front, but you can also just write it like this, x cubed over 3. And then minus 3 halves x squared, right? We increase the power of 1 by 1, bumping it up to 2, and then divide by that new power. And then plus 2x. And this is being evaluated from 0 to 1. And then subtract, it's going to be this same exact thing, so I'm just going to copy and paste. Same exact thing, and then we're evaluating this guy from 1 to 2. And then we're going to add the same exact thing, but this last one is evaluated from 2 to 4. As we begin to evaluate this, notice that we'll have to plug in 1 for 2 of these terms, and we'll have to plug in 2 for 2 of these terms. So as long as we're careful, we'll be able to reuse some of our work, but let's be very careful. Let's begin by plugging in the upper bound of 1. Plugging in this upper bound of 1 is going to give us 1/3 minus 3 halves times 1 squared, so just minus 3 halves, and then plus 2 times 1, or just plus 2. We would then subtract, plugging in the lower bound, but that would just zero everything out, so we actually don't have to worry about that. Since we're going to have to plug in 1 again over here, why don't we just go ahead and simplify this before we go any further. 1/3 is the same as 2/6, and then we're subtracting 3 halves. That's the same as subtracting 9 over 6. And then adding 2 is the same as adding 12 over 6. 2/6 minus 9/6 plus 12/6 is 5 over 6, so let's just replace this with 5 over 6. Now moving on to the second term, we are subtracting this one. Remember, this is representing that negative area that the absolute value switches to positive, which is why we are subtracting it. All right, let's plug in that upper bound of 2. That's going to be 2 cubed over 3, which is 8 over 3. and then 2 squared, which is 4, times 3 halves, so that's going to be 12 halves, which is 6, so minus 6. And then plug 2 in here, that's 2 times 2, so plus 4. And then subtract, plugging in the lower bound. We already know, though, that when you plug in 1, what you get is 5 over 6. So minus 5 over 6. That is the second term. Now, remember, we're going to have to plug in 2 over here as well. This is what we got when we plugged in 2. Why don't we go ahead and simplify that? Negative 6 plus 4 is negative 2. And 8/3 is the same as 2 plus 2/3. So this is actually just 2/3. So I'm going to delete all this. When we plugged in 2, what you end up getting is just 2/3. All right, moving on to the last set of brackets over here. We have to begin by plugging in the upper bound of 4. 4 cubed is 64, so we have 64 over 3. Why don't we just go ahead and reduce that right now? 3 goes into 64 21 times with 1/3 left over. So 21 plus 1/3. All right, then plug 4 into this. That's going to be 16 times 3 over 2, which is 3 times 8, so minus 24. Plug 4 in here, that's going to be plus 8. And then we have to subtract, plugging in the lower bound. The lower bound is 2. We know that when we plug in 2, what we get is 2 over 3. So minus 2 over 3. Finally, bringing this all together, let's collect the whole numbers first. So 21 minus 24 is minus 3, plus 8 is positive 5. Now we'll collect all the fractions with a denominator of 6. So we have 5 over 6. And then minus 2 over 3, so minus 4 over 6. And then minus negative 5 over 6, so plus 5 over 6. And then plus 1/3, so plus 2 over 6. And then minus 2 over 3, so minus 4 over 6. At long last, this is 5 plus, if you simplify the numerator, you're going to get 4. So 4 over 6, or 2/3. You could write this as an improper fraction, 17 over 3, or write it as 5.6 repeating. Moving on to problem 15. I cannot tell you how happy I am that we are done with the definite integrals. From here on out, it's indefinite integrals. Let's get into it. This is just going to be so relaxing and so wonderful. We begin by rewriting this, so we just have powers of x. First, we've got this square root of x cubed. That's the same as a power of 1/2. So if we have x cubed in a square root, that's the same as x cubed to the 1/2. We also have the cube root of x squared, which is the same as x squared to the 1/3 power. Just like a square root is a 1/2 power, a cube root is a 1/3 power. So we're integrating this with respect to x. Now we just have to apply our exponent rules. X cubed to the 1/2, just multiply the exponents. So that's x to the 3 over 2. And then add x squared to the 1/3. Just multiply the exponents. That's x to the 2 over 3. Now that we just have powers of x, we can proceed with the integration. First, we have to increase the power of x to the 3 halves by 1. To do that, we just add 2 halves to the exponent. So it now is x to the 5 halves. But then we must divide by the new exponent. Dividing by 5 halves is the same as multiplying by the reciprocal, 2/5. Similarly, we must increase the exponent here by 1. To do that, just add 3 over 3. Again, it's just like adding the denominator to the numerator. Turns out to be 5/3. So we have x to the power of 5/3, but we're going to have to divide by that new exponent. That's the same as multiplying by the reciprocal, 3/5. This is an indefinite integral, so then just throw on the arbitrary constant of integration plus c. Moving on now to problem 16. This one we can jump straight into the integration with because we already have just a sum of powers of x. Maybe we want to put this in parentheses to make it really clear what we're integrating. Only thing you have to be careful of here is that negative exponent. First, let's worry about x squared. You should be able to do this real quick by now. Increase the power by 1 and then divide by the new power. There you go. As for x to the negative 2, similar thing. Increase the power by 1 from negative 2 to negative 1, right? Adding 1 to negative 2 gives you negative 1. And then divide by the new power. Dividing by negative 1 just switches the sign, so instead of writing that plus, let's just write minus, and then add the arbitrary constant. By the way, it's worth mentioning, if you don't already know, that the integral of x to the negative 1 cannot be evaluated with the power rule. This actually turns out to be the natural log of x, which maybe you're aware of already, maybe not. If not, you'll learn about it soon. But just so you know, you can't apply the power rule to integrate that. We can integrate up to it like we did here. We integrated x to the negative 2. But you can't integrate x to the negative 1 using the power rule. If you tried, the new power that you're dividing by would be 0. Obviously, that's not going to work. Moving on to problem 17, the integral of x times the cube root of x plus the fourth root of x. We'll begin by rewriting the radicals, the cube root and the fourth root, as rational exponents. The cube root is the same as a power of 1/3, and similarly, the fourth root is the same as a power of 1/4. Now we can just distribute this x out here. This x has a exponent of 1, so when we multiply it by these other x's, the exponents are just going to add together. So it's just going to add 1 to both of those fractional exponents. So this is equal to the integral of x times x to the 1/3 is x to the 4/3. And x times x to the 1/4 is x to the 5/4. Remember, this isn't the integration part, right? We happen to be adding 1 to the power just because we're distributing x here, but this is not the integration part. Now we're at the integration part. Now that we have just terms of x to some power, we can go ahead and integrate this. We'll begin by increasing this power of x by 1. So add 3/3 to it, and it's going to become 7/3. So x to the 7/3, divide by the new exponent, or multiply by its reciprocal. Now increase this power of 5/4 by 1. That's going to become x to the 9/4. And then divide by the new power, which means we multiply by the reciprocal, and then add the arbitrary constant. On to problem 18. We'll begin this one by splitting up this fraction across the subtraction that's taking place in the numerator. So we'll have 4x divided by the square root of x, but let's rewrite the square root of x as just x to the 1/2. And then we're subtracting 3 over the square root of x. But again, let's rewrite the square root of x as x to the 1/2. All right, now we can simplify these exponents a little bit further. 4x over x to the 1/2, just subtract the exponents. The exponent of 1 minus the exponent of 1/2, because it's division. So in total then, it's just going to be 4 times x to the power of 1/2, because 1 minus 1/2 is 1/2. This x to the 1/2 is in the denominator, and we can move it into the numerator by making its exponent negative, so x to the -1/2. And now we are ready to integrate. So increase this power of 1/2 by 1, thus we're going to have 4x to the power of 3/2. We need to divide by the new exponent, or multiply by its reciprocal. Its reciprocal is 2/3, so this would be 4 times 2/3. That's just 8/3, so let's write it as 8/3. And then we have to subtract, increase this exponent by 1, so -1/2 plus 1, that's going to become x to the +1/2. And then divide by the new exponent. Dividing by 1/2 is the same as multiplying by 2. Remember, we still have this factor of 3, so we're just multiplying that 3 by 2, so it's just 6. Of course, we still have that negative there as well. Finally, add on the arbitrary constant, and there you go. Moving on to problem 19, the integral of v times v squared plus 3 squared with respect to v. All right, to carry this one out, we're going to have to distribute the v squared plus 3 times v squared plus 3, and then we'll have to multiply that by v. Once you learn what's called u substitution, there's actually a quicker way you could do this without doing all of the expanding, but for now we're going to have to do the expanding so that we can use the power rule. So we have v times, hopefully you're pretty quick at expanding squared binomials, v squared plus 3 squared is going to be v squared squared, which is just v to the 4, plus 3 squared, which is just 9, plus 3 times v squared times 2, so 6v squared. We're integrating this with respect to v. Now all we have to do is distribute this v through the parentheses, which is just going to add 1 to these v exponents, and then of course this 9 will become a 9v. So where we did have v to the 4, we multiply it by v and now have v to the 5. Where we did have 9, we now have 9v. And where we had 6v squared, we multiply that by v to get 6v cubed. And now we can proceed with the power rule. Increase the power of v to the 5 by 1, so it's v to the 6, and then divide by that new exponent. Increase the power of v to the 1 by 1, so now it's v to the 2. We still have the factor of 9 in front, and then divide by the new exponent. And then we have v cubed, increase that power by 1, so v to the 4, and then divide by the new exponent. 6 over 4 is just 3 over 2, so let's write it as 3 over 2. And don't forget the arbitrary constant plus c. Alright, we've come to the end of the road with problem 20, the integral of the square root of 8 over x. We did a problem very similar to this one earlier. We're just going to separate the fraction a little bit here, taking the square root of each thing individually. So this is the same as the square root of 8 over the square root of x. But then, of course, remember the square root of x in the denominator is the same as x to the 1/2 in the denominator. But then we can get it out of the denominator if we write it with a negative power, x to the -1/2. Now that we just have a power of x, we could take this square root of 8 out if we want, but it's not really causing any problems. I'll just leave it there. Let's go ahead and integrate now with the power rule. Increase the power of -1/2 by 1, so we're going to have now x to the +1/2, and then divide by that new exponent, divide by 1/2. But that's actually the same as multiplying by 2, so in fact this is just 2 root 8. Don't forget the arbitrary constant, and don't forget to notice that we can simplify the square root of 8, because 8, of course, is the same as 4 times 2, so we can actually take the square of 4 out of the square root. It's just 2 root 2. So we have 2 times 2 root 2, which is actually just 4 root 2. So let's go ahead and rewrite that as 4 root 2. And there is our final answer. Here is one last scroll through the problems and solutions for your reference, and I will show you the bonus problems now. Here are 10 more bonus problems, and you can see 5 of them for free. If you find my lessons helpful, I hope you'll consider supporting Wrath of Math by becoming a channel member, and then you can access the solutions video for all 10 of these harder problems. A couple fun things to point out: this one has an irrational exponent. This one has an x in it, but we're integrating with respect to v. And this one is an integral of an infinite sum that's actually equal to e to the power of x. So a lot of fun examples. Let me know in the comments if you have any questions, and be sure to check out my Calculus 1 course and Calculus 1 exercises playlists in the description. If you join the channel, you can see the solutions for these 10 problems, as well as other exclusive calculus content. Thanks for watching.
I'm the mathematical menace, the machinations of mankind. Two calculators at the same time, hand signs and abacus, finger count and calculus. I'm a V to the T, my parameter the rapidest. Happens like this, my lecture's the most prominent, dominant. Call me De Morgan, I get the compliments. The union in together like any time that we intersect, cause my opponent